So of course, if you made it to engineering mechanics, you already passed your physics classes and you have a understanding of vectors, and you've seen it in mathematics classes as well. Let me reiterate it anyways, just so that we're all on the same page. So first of all, vectors have a direction and a magnitude, right? Direction plus magnitude. And that is important because some physical concepts cannot be explained by just a number. In fact, let me make a side note here. If you have just a single number like a scalar, then you can describe things like temperature. You can describe things like mass, and so on and so forth. However, if you talk about forces, they have not just a magnitude, like the mass does, for example, it has also a direction. And therefore, you need to use at minimum vectors. Therefore, it's important to really identify them properly. So here in the lecture, you always have to identify them with an arrowhead, or some people also put a single line underneath it. In a book, you would probably find a very bold-faced letter, right, like this. But here in the lecture, I will use something like A to describe a vector. Or if I would be really neat, I probably should do this. And that is important to differentiate from something like this, because that would be just a scalar, and that is physically very different than a vector, and so you are encouraged to always properly identify that. So do not use this for vectors. Always show that there is actually an arrowhead above it. So the direction is usually given by a plus or minus sign. And the magnitude is usually the length, and it's also positive because the length is always positive, right? So magnitude always positive, which is the length. And then let us real quick remember that when we draw them, what is what entity? So for example, if I have a coordinate system here, I have a vector in that coordinate system, and pretty much this is the length, and the direction is given here. So that I can describe it by the angle alpha that it has relative to the horizontal most often. And keep in mind that this part here we call the tail, and this here we call the head. All right, so now we obviously recall what vectors are, and we probably also recall the basic mathematical rules. So if you multiply it with a scalar, for example, then let's say you have something like the scalar a times vector a would be nothing else than a times ax, a times ay. And today is the last time we write vectors like this. Some of you do that. I will come back to that. I'm just going to use this right now, this notation, because that's what most of you are used to. However, this is no different than ax and ay. And that means that we can, of course, multiply the individual components by the scalar. And if you know how to multiply, then you can also do division, because if you, let's say, you have a divided by b, then that's just the same as 1 over b times a. And so therefore it's the same rule, which is 1 over b times ax and 1 over b times ay, and so on and so forth. But of course, we do remember this. In engineering mechanics, of course, we usually deal with forces. So let's say you have, for example, 5 times 7 8 newtons. And so that would equate to 35 and 40 newtons. Let's talk about vector addition, which is a little bit more fun, and that is because we have a visualization problem here. So let's say I have a tabletop, and on that tabletop I will place myself at point 0. So this is point 0. And now I'm going to walk on that tabletop. And I'm going to walk along this line. So this is where I walk. I call that vector Raphael. But now there's a student who may not like me or something like that and wants to try to pull the table in this direction. And so every point of the table really moves along that direction, so that the table ultimately ends up somewhere like here. Including the starting point. Right? So that the table at the end is in a different location. So I can actually use the arrow and move it parallel so that now it's here. And if both happens at the same time and you stand here and you watch at the system or you look at the system, then what you would see would be pretty much vector addition, which would be this arrow here. So if I call this here student, then the red vector here would be R plus S. And of course they are vectors, so I should follow my own rules here. And so vector addition is really nothing else than combining the two vectors to form the third one, pretty much as it was visualized here. However, it's an important aspect that we will use in engineering mechanics, so therefore let's talk a little bit more about it. So you probably have done the vector addition before, and you may have used one of two methods. And one method is called the head to tail technique. So head to tail method or technique. And the way that one works is if you have two vectors that are somewhere random in space and relative to each other, and keep in mind that you can always move vectors parallel along their own line, right? So let's say I have vector A here and vector B here, and now I can move them parallel. I'm going to use a different color for one of them so that you can better follow that. So I'm going to move the first one parallel, and I'm going to move it head to tail. And of course, this has to have the same length. So this here is vector A. And now my resultant vector, similar to what we actually seen before, in fact, we kind of used this in our first example, is shown here now. So this is what we called F resultant before. Here, let's call it vector C. So that's the head to tail technique, and that always works. In fact, you may want to also know that you can do it the other way around. So for example, you could have the blue vector somewhere down here, which was called vector A. And then you can actually attach vector B to it. So let me get that parallel. And let me move that so that it will fit. So this now would be vector B. And of course, they have to be identical to each other. So A plus B is equal to B plus C. That's really the story that I'm trying to send here. So let's write that down. So A vector plus B vector is equal to B plus C. And that is an important rule that applies to vector addition. There is another technique called the Parallelogram Technique. And that is very similar to also what we've seen before. So let's have our two vectors again. I have vector A and let's say a vector B. So this is B, this is A, and now I use my parallelogram technique where I just move each of these parallel to each other. So I would have this B parallel, and then I'm going to move A parallel. And where those meet, or the diagonal along the parallelogram, is really my resultant force. So I have a resultant force here, or any resultant really. I'm going to call that C. A vector and B vector. And once again, this rule up here applies because it doesn't matter in which direction you do that. So please keep that in mind. A plus B is equal to B plus C. Now, of course, you can do that multiple times or consecutively. And my favorite examples for this is when I take my animals for a walk. So let's go on a walk with my animals. Let's say I'm standing right here. This is my starting point, Raphael. And I'm bringing my dog. And my dog is very strong and it pulls me in this direction. So let's call that a dog. But I also have two cats, so I'll bring these two. So here's my cat 1. And let's say the other cat is a little bit more afraid. So let's say that she wants to move in this direction. And maybe I'll even bring my hamster. I guess my hamster should be a little bit weaker than the rest of the bunch. And so now the question is, where will I go if all these animals pull on me in that direction as shown here? And the answer is you can use the head to tail technique or the parallelogram technique multiple times. I'm just gonna show you how that applies. I'm gonna start with my dog, and then just to be random, I follow by cat 1, by cat 2 I should say. So that would mean that I move in this direction. And then the hamster was going in this direction. And the cat moves in this direction. And ultimately, I, Raphael, would be pulled in the direction from my starting point to the end point of that head to tail method. So this is the direction I would be pulled. Of course, if this is called the action force, right? So that's the action that the animals apply to me. However, if I want to somehow resist that, and I want to stand still, I have to apply Newton's third law and actually pull in the opposite direction. So this would be reaction Raphael. And so therefore, you now understand how to add multiple times the vectors. Of course, numerically, there might be smarter ways to do that, but this method always works, and that goes hand in hand with vector addition. And with that, I believe we're now ready to talk about vector subtraction. So let's move on. So vector subtraction is actually no different from vector addition. In fact, let's ask ourselves, what is a negative vector? So a negative vector is a vector that is parallel but opposite in direction. So let's say I have vector A here and I want to know what the negative A is, then it would just be minus A. And so now, if you know that, you can actually use the same technique, right? Because you have, let's say, A minus B vector would be nothing else than A plus minus B. And so let's have a sketch for that as well. Let's say I have a vector A, and I have a vector B, and let's say that is here. And now I want to know what is A minus B. So I take my B and turn it into minus first. So that would pretty much look like this. So this would be minus B. And now I have to use the head to tail technique. I guess I'm going to do that a little bit on the side. so that I do not end up in my own drawing here. So let me move this. And now I can add my negative vector via the head to tail technique in this direction. So this is minus b. And so my ultimate c vector now has to go from the starting point to the end point of this. So this would be c. And so c is equal to a minus b. But also notice that c plus b is equal to a. Of course, this is just rearranging the formula. But it can also be seen here that if you have c plus b, you end up with a, right? B would be in the opposite direction of negative b, and so therefore c plus b would be a. And that concludes vector subtraction. We should now have a good understanding conceptually of that. So let's move on to vector decomposition. And why is that important? Because often you actually have to do the reverse. Instead of adding two vectors, you have to break them down into their individual components. I'm pretty sure you have seen this before, but let's talk about it anyways. So we have an x-axis and a y-axis, and within that y-axis and x-axis we have a vector, and that vector could be randomly arranged. So let's call this here f1. And of course we know from high school that we have these components here. This here would be usually what we called f1x. And then we also have the value from here to here, which we will call f1y. And many of you are probably used to writing that f1 is equal to f1x, f1y, and then using curly brackets. But that is something that from now on we will never use ever again. We also won't use something like f1x, f1y. Also a very common method to write this down for students who came just out of high school or who came from other fields. But this is not what we use in engineering. This is from now on point deduction. And why is that? Because of something you have seen before, and that is called the base vectors. And the base vectors are mutually perpendicular to each other, and they have a length of 1. We will write this down in just a second. So this is different from a unit vector. It is a unit vector too, but we have a base vector called I hat and j hat, and I hat clearly goes along the x-axis, whereas j hat goes along the y-axis. And those define the vector space. And let's write that down, that I hat and j hat are the base vectors in 2D. And those define our vector space. And therefore, from now on, we will always write our vectors, f1 for example, as f1x multiplied by I hat plus f1y multiplied by j hat. And we put that in parentheses, and then we usually put a unit behind it. Let's say this is a force, so that you always represent these vectors this way. And let me explain that. So this here would be a scalar, right? This is a scalar quantity, whereas this is a vector. And same is true here, scalar and vector. And the reasons engineers prefer this is because they can avoid dealing with vectors whenever possible, or they can do scalar operations on the components. So let's memorize that from now on we will always write our results in this format, or all our vectors in that format, so that we can deal really with only those quantities, vector quantities, when we really have to. You of course know already that f1 is really the magnitude f1x squared plus f1y squared. This is Pythagorean, and this works in 2D and in 3D, and so that is something you need to always have under your belt. And here I forgot my vector sign, but now it is complete. So let's look at that. And last but not least, for vectors, you always will need a direction, right? So you will always have to define the angle alpha here, let's call it. So let me include that. Let's say the angle alpha here, alpha. And of course, in this particular case, because we're in the first quadrant and we're measuring from the horizontal axis, alpha is really equal to the tangent of, or the inverse tangent of f1y over f1x. So that's rise over run. However, sometimes that leads to incorrect results. So be careful when you use this formula. And I encourage you to think about what happens if you use this formula in the second quadrant, what happens if you use it in the third quadrant, what happens if you use it in the fourth quadrant. These angle alpha will come out differently. And memorize that we always measure from the positive x to the positive y-axis. So let me give you one example, although I want to encourage you to think about this yourself, but because this goes wrong so many times on exams, let me just show you what happens if you have a force in the second quadrant. So let's say we have an x, y coordinate system here, and your force is really acting in this direction. If you now use the tangent function, you will not find the angle that's relevant. You will actually find this angle here. You would find this alpha, because rise over run will give you that enclosed angle. But what's really asked of you at all times is this angle theta. So that is something you need to keep in mind. And again, please be aware that depending on which quadrant you find your resultant in, this will be different and you have to interact differently with that. But that completes the vector decomposition, and please understand that from now on you will always write vectors like this. You will also include the magnitude and you will include the direction. In fact, let me underline that as well, because you need to memorize that every result that you present for vectors will always contain 3 pieces of information. So results for vectors always include 3 sub-answers. So it's not really complete if you forget either one of them. Don't get me wrong, you can also use unit vector instead of the angle, for example, but you always have to have 3 entities. You have the components, you have the magnitude, and you have the angle. And that is always the minimum you have to report. But I believe that concludes our vector decomposition, how we will act with that here in engineering mechanics from now on. And so now we are ready for our examples.